Hi everyone, welcome back to workshop, and it's repair time again, and this time I've got a Fluke 8846A 6.5 digit multimeter. Now these are really nice multimeters. They've got a really nice display, although I'm not sure you can see it too well because it's still got the cellophane across the front of the display. So I would suspect this meter hasn't seen much action in its lifetime. Now I do actually have it connected to my PDVS2 Mini here, set at 1 volt, and as you can see it's actually quite accurate. It's down to, well, almost spot on there in the 1 volt range. But it does actually have a fault. And the fault is actually on the resistance mode. If I just put it in resistance mode, you can see it's sitting with 76.7 k ohm without anything connected. And if I do actually connect up a short across the inputs, it does change. It does go down to 0 ohms or thereabouts, but open circuit, it just does some weird and wonderful things. Let's try 1k. It's reading about 0.6 of a k, so it's all over the place. So before I actually tear it apart, I did actually go ahead and test some of the other functions on the meter, and DC current's working in the 10 amp range, but I'm getting absolutely nothing in the 400 milliamp range, so probably a blown fuse there. So let's tear it apart and let's see what we can find. Okay, so here we are inside the unit. Now unfortunately I'm not able to pick up the schematics for this unit. I did actually try contacting Fluke themselves, gave them the story, and nope, still can't get the schematics out of them either. So really I'm going to have to troubleshoot this one in the dark, as it were. However, I think I've managed to build myself some sort of idea of what the problem may be. Now what I'm thinking is that the meter's probably got a precision current source, an adjustable current source that's used over the different ranges of the resistance mode on the unit. Now here's an example from a completely different multimeter. Actually, it is actually a Fluke, but it's a much older Fluke. And you can see what's going on here. You've got a precision voltage being generated by this op amp here, goes away off here, and you've got a programmable current source down and along here. These analog switches and resistors basically switch in and out to change that programmable current. And it's done by a bunch of analog switches. Over here you can see them, software controlled, and you've got 1, 2, 3, 4, 5, 6, 7, 8 switches. Now looking at the unit here itself, we do actually have an analog switch, a DG444, and right next to it an op amp or two. So I really want to have a look at this op amp here. We do actually have another one over here. So let's have a look at that part of the circuit. Let's do some measurements and see what I can pick up. So first things first, I've managed to pick up a suitable ground point for my multimeter here. And let's measure the supply on this op amp over here. So it's an LF353, an old school op amp. Pins 4 and 8 are the supply pins. And you've got plus 15 rock steady, and over in pin 4, if I can just get onto it, minus 15 rock steady. And over on this side here you've got another LF353 measuring the supply pin there, plus 5.6 but not very stable, and over on pin 4 minus 5.4 but again not very stable. Now the curious thing is, if I put the multimeter in a different mode, it's currently on DC voltage, if I stick it on ohms, the resistance mode, and measure the same supply, now we're up at 16 volts for the V plus on that op amp, and minus 14.5 and jumping around. So it looks like the supplies to the op amps are controlled. Probably this bank of FETs over here are switching in and out the various supply pins onto those op amps. Now the analog switch is the same thing. If I look at pin 4, that's the negative supply to that analog switch. Minus 14.7, fairly stable. Let's go into DC voltage mode now. Minus 14.9, fairly stable. AC voltage. Minus 14.6. Well, so the negative supply is moving around a little bit. Now let's look at the supply pins to that analog switch. Well, there's two supply pins. One of them's for the logic side and the other one's for the output side. So I think this pin here, pin 12, is the logic supply, 5.1 volts. That makes total sense. And the other supply pin, 15.7. And if I just go into DC voltage mode, it jumps down to 14.9, 14.7 for the AC voltage mode, and in ohms mode, 15.7. So I'm not convinced that's correct because the voltages are all roughly around about the same. Now I don't think that's right, because I wouldn't have thought that supply voltage to the IC would have to change by that small amount. Fair enough if it was switching between 5 volts, 10 volts and 15 volts, something like that. I could go along with that, but not when it's just 14.5, 15.5, that sort of thing there. I'm not convinced. Well, looks like I might be down a rabbit hole in terms of the functionality of the analog switch. So let me show you what I found. So here's the data sheet for that DG444, and as you can see, 4 analog switches there, and these are the control inputs here on pins 1, 16, 9 and 8. So what I've gone ahead and done is I've mapped the actual 4 logic pins of the analog switch against the function that the meter's in. And as you can see, in any one mode, only one of them is low. So I think the analog switch is purely for the control of the various functions of the meter. It's not specifically for the current source. Well, a little bit more digging on that 9 SOT23 packages as I've depicted here, and actually it's a mixture of NPN transistors, 18 volt Zeners, 6.8 volt Zeners, a diode and another type of NPN transistor. So not exactly sure where they're being used, but given that you've got 18 volt Zeners and 6.8 volt Zeners involved, I somehow think that's got something to do with the supply switching that we were seeing on the op amps and also that analog switch there. Well, a bit more of investigation, and there is actually another 2 analog switches over here, 2 more DG444s. However, I'm not so sure they're related directly to the resistance mode, because bringing my diagram here, you can see the 2 ICs that sit more or less side by side, and the 4 enable pins for each one of the analog switches are at the 4 corners of the chip. Very handy for scoping, etc. And you can see that they're used for various different functions on the front panel there. AC voltage, DC current, AC current, DC current in the milliamp mode, 10 amp mode, and you've also got the 2-wire resistance mode over here, which is shared with the DC voltage, and the 4-wire resistance mode up here. So yeah, I don't think they're directly used, not like that diagram for that older Fluke that I've got anyway. Well, it looks like we're getting somewhere. Let's take a closer look at this part of the circuit down here. Well, I've kind of convinced myself that the problem does indeed lie around this area. We've got a couple of op amps there, as I said earlier. They're dual channel op amps, and this right hand op amp, one of the outputs is active when I change the resistance coming into the front of the meter, and it's only changing the resistance that will affect the pin. Any of the other modes, voltage, current, etc., don't do anything. But that's about as much as I get out of these op amps. The other op amp does absolutely nothing, and it's stuck. I wouldn't say it's hard against the rails, but it's pretty high on its outputs, and it doesn't seem to do much. However, comparing the inputs to the outputs, I would say it's doing what it's supposed to do. So I'm not really sure what's going on here without actually tracing the circuit out. You know, if only I had another Fluke 8846A multimeter to compare some of the signals with. Maybe like this one here. Actually, this is another faulty one, but this one's got a catastrophic fault with it, which means I can't power it up in its current state. So what I think I'm going to do is I'm going to switch tact here, and I'm actually going to make a quick attempt to see if I can repair this one, because it might be pretty easy. Let me zoom in and show you the fault that is very apparent with this meter. And there it is down there. This IC's got a hole, a burn hole, right in the middle of it. But you never know, perhaps removing this IC and replacing it, the meter might come back to life. Of course, what will be in question is the actual power supply circuit, and perhaps maybe some of the other ICs have been damaged as well, because a catastrophic fault like this with a hole in the top of the IC is usually down to a power supply problem. So let me clear the original 8846A away from the workbench. Let's get this one down and let's see if we can make a repair. So both of these ICs here are exactly the same. They're HCT 4053s, which are a 3-channel analog multiplexer IC. And going across the supply pins, I'm getting about 87 ohms off camera. Now measuring the other 8846A, it should be in 1 or 2K, something like that. So yeah, something's shorting out the supply, and at least off the bat it's going to be this IC here. So just to save this Fluke resistor array, I'm just going to put a little metal guard in front of it. And let's get the heat on. And there it is, removed from the board. Let me clean up the pads, clean up the PCB, and see what we're left with. Right. That's IC removed, pads cleaned up, and the circuit board's cleaned up pretty well. I think we're good. But the big question is, what have I got across the supply? So let's just go into this IC here. And 0.8 of a K. That's certainly a lot better. Whether that's good enough, I'm not really sure. It is a different rev of circuit board. It's a slightly older board, a Rev 18 as opposed to Rev 20, so I'm not really too sure what sort of differences there are, but 0.8K is still a little bit lower. Well, on second thoughts, that resistance across that supply is about half of the other meter, so I'm actually going to take the circuit board out. Let's take another look at the back. I've had a good look over this top side, and I can't see any other burnt out ICs or tantalums or anything like that. And my checks in and around the power supply area don't reveal any shorts anyway on either the input or to the output of the regulators. There's all manner of different types of regulators here. There's LM317s, LM337s, etc. So I think I'll take the circuit board out. Let's take a look at the underside of the board and let's double check that. And I'm also going to try and track down where I'm getting that low impedance across that supply rail. Well, that's the circuit board out, and there's nothing obvious, and as suspected there is quite a lot of components on the bottom side. Bridge rectifiers, some diodes, Schottky diodes I think, and an IC there, and a bunch of tantalums. But going over those components, They're not dead short or anything like that, so still a little bit curious as to why I'm getting a low resistance across that 5-volt supply. I don't really want to put power into it until I know what's going on, even if I am ramping it up from 0 volts AC on the mains input. I really want to find out if all these different regulators are working okay. Okay, got my bench power supply hooked up, set it on channel 1, going direct to the board, 300 milliamp limit, and I can go up in low voltage steps, and we'll monitor the current here, and we'll see what the regulators are doing on the board. Okay, and I've picked up a ground point here, and this red wire here, that's on the input to the first 5-volt LM317. So let's just see what it does. I've got my multimeter here. Okay, 1 volt, and we're drawing about half a milliamp. That's good, and we're starting to see a rise there. So let me just take it up slowly. Yep, 5 milliamps, 30 milliamps, 72 milliamps, 125 milliamps. We're getting closer to that 5 volts. 160 milliamps at 6 volts coming in. 7 volts coming in, 190 milliamps, and we're achieving 5 volts. So let me just go a step further and make sure it's regulating. 8 volts, 200 milliamps, and we're staying at 5 volts. So that 5 volt regulator is okay. And we're up at 9 volts now. Yep, 5 volts, 210 milliamps. I think that one's fine. Right now, before we move to the next regulator, I do want to put the thermal camera on it just to see what that 5 volt rail is doing. It's still on at the moment. I've got 8 volts coming in. 200 milliamps is what it's drawing. I'm getting my 5 volt regulation, and 200's okay. I think that might be quite normal, but it's not like it's 1 amp or something like that. But whilst we're here, let's get this thermal camera on it. Let's just check for any hot spots that might be pulling that current a little bit higher than it should be. And I've picked up a problem. Right down here, there is a huge heat spot there. And this IC here is absolutely burning hot. So we've definitely got a problem there. And the rest of the board looks fine. So yeah, definitely got a problem down there. And the IC in question is a DG444. That's an analog switch. Not really surprising that that's gone. If any IC is going to go, in my experience over the years, analog switches were always prone to failure. Just get the supply slightly wrong, slightly more than it should be, or whatever, and they're very easy to blow. So let's get that one off the board, and let's see if I've got a suitable replacement. Well, that's the IC removed from the board, but I've still got the supply hooked up, so I'm actually going to power it up just to see if what sort of difference it makes to that current consumption now that I've removed that IC. So let me just wind up the voltage off camera. Now it was 8 volts, I was getting about 246 milliamps draw, and we're now getting 54 milliamps. That's looking much better. Well, I'm not sure if you can see that, but there is a slight discoloration on the centre of that DG444. Very, very subtle. In fact, I think it's coming up on camera a little bit better than it is by the eye. So yeah, telltale sign that that IC's knackered. So the next thing I'm going to go for, we've got another LM317 and 337 pair here. And they're generating the positive and negative 20 volt supply. Now there is actually a positive and negative 15 volt supply here, but they're not using regulators. I think they're using a couple of transistors, FETs there, and I think they're probably being driven via the 20 volt supply. So I'm going to hook up the 20 volt, the positive 20 volt regulator first, and I'll monitor the various other voltages as we wind that one up. Right now, because I'll be monitoring quite a number of voltages possibly, I have actually created a little diagram of that area on the PCB with all the regulators, etc., and where I can pick up very easily the various supplies. Well, as you can see, I'm getting 20 volts exactly on the multimeter there, and that's the output from this LM317 here. I've got 24 volts going in, and it's drawing about 20 milliamps, so that's absolutely perfect. Now, I've actually probed the other DC supplies, and they're not doing much at all. The plus 15 volt rail here is just sitting at about 1.1 volts, so whether that's a problem or whether the plus 15 volt rail comes from its own secondaries on the transformer, I haven't traced that out yet. But at least that 20 volt rail, perfect. So I'll go off now and try the negative 20 volt rail. And there is the minus 20 volt rail. I'm getting about minus 20.3 coming out. I've got minus 24 volts going in, and it's drawing about 71 milliamps, so a little bit more than the positive 20 volts, but it's probably okay at 70 milliamps. And again, I'm not getting anything on that negative 15 volt rail, so as I said earlier, it's probably because it's on a different set of secondaries. Okay, and here we go. I'm on the tag of that LM317 because that's the output pin, and we're ready to start ramping up the voltage. And you can see it's starting to come up now, 0.6 of a volt. I'm only got 2 volts coming in at the moment. No, my mistake. That's the positive 1.5 volt regulator down there, not the 3.3. It's got some silk screen on the board. It's marked 3.3. But, no, looking at my little drawing, that LM317 is for the 1.5 volt rail, and that's exactly what I'm getting. 4 volts coming in, 1.5 volts coming out. Perfect. 240 milliamps, that might be a lot for the 1.5 volt rail, but I suspect that's powering all the microprocessors, etc. over here. Quite a low power. It's a relatively new board, a new design, something like 2004 or something like that, 2005, so it could be using 1.5 volt logic. Okay, so I went and identified some of the parts in and around that MOSFET that generates the plus 15 volt supply, and you've got the actual MOSFET itself. It's a P-type MOSFET. And there's a few other SOT23 devices and an LM358 op-amp. The SOT23s are a Schottky, a voltage reference 2.5 volt shunt diode, and a switching diode. And those 3 devices all seem to be okay. However, I have identified a problem. The LM358 is not getting any power. Now, I did power up the negative 15 volt rail and just had a look at the op-amp there, and it seems to be getting power from the unregulated supply coming in. So I would expect the plus 15 volt rail to do the same. Now, there's nothing getting hot in and around there, so let's take a look at the supply pin of that LM358 and see where it's coming from. Okay, found the problem, and there is no problem. The op-amp on the negative 15 volt rail is powered by the negative 20 volt regulated DC supply. However, the op-amp on the plus 15 volt rail comes from an unregulated DC on this electrolytic cap here, which is derived from one of the secondaries via this header here, which I obviously don't have powered up at the moment, and it works out at about 28 volts DC. So there's a slight difference in the circuit there. So obviously without that supply, I'm not getting an op-amp supply, and that's why the 15 volt rail is going higher than it should do. So I think it's probably okay. Let's move on. Well, I think I've tested about as much as the DC supplies as I can. So I've got 3 ICs to put back on the board. I've got the 2 that I removed earlier and this analog switch down here. Now, very luckily, I've got stock of all of them, including the analog switch, the DG444. And the reason for that is I think I bought these when I was repairing the Keithley 2001 multimeter. I knew I'd had some somewhere, so I've got a couple, so no problem. So let's go fit those ICs now, clean the board up a little bit, and we'll try hooking it up to the secondaries on the transformer. Well, I think it's about time to actually put power into the board from the transformer. Now I'm going to wind the supply up slowly via my rheostat. However, one thing to note, I haven't actually tested the supplies on the isolated section of the board at the back there. There is a couple of regulators there, and it generates a 5 volt supply, 3.3, 1.5 volt, and I think a 60 volt supply for the actual backlighting on the display. So I haven't tested any of that, so there's a lot to monitor as I put power in and wind it up slowly. So what I'm going to do is I'm going to disconnect the secondaries for the isolated section of the board there, and I'm just going to concentrate on this side here. Okay, and here we go. So I'm going to start off with the positive 5 volt. Let's just see what happens. As I turn it up, yes, we are getting a DC supply. So the fuse on the back of the unit is not blowing now, not yet anyway. So I'll just leave it at that, 2 volts, and let's check some of the other voltages. Yeah, minus 5 is sitting at 2.2. Minus 15 sitting at minus 3. Plus 15 sitting at 1.8. 1.5 volt hasn't started to rise yet. So let's keep going. 3 volts on the plus 5. 4 volts on the plus 5. Now up to 5 volts, and we're about 100 volts AC coming in. Let's just check the minus 5. It's okay, minus 5.2. Plus 15 volt rail. 6.4, the minus 15. Minus 1.5. Not sure about that. Plus 20. It's plus 8. Minus 20. Minus 8. So let's turn it back down and let's just check the board now for any hotspots. The ICs are replaced, are stone cold, so that's looking good so far. Not feeling anything. The regulators are all stone cold. Transistors are stone cold. Yep, so let's carry on. Back on that plus 5 volt rail. So back up to plus 5 volt again. Yeah, plus and minus 5 are fine. Let's try and get that plus 15 volt up. No, the minus 15 volts not doing anything now. Not liking that at all. Well, I don't really know what's going on with those plus and minus 15 volt supplies at the moment. It could be that there's some sort of inhibit. Now that I've got the rest of the board sort of powered up, it's affecting that part of the circuit, because I mean there is a couple of op amps there, and it begs the question, you've got LM317s and 337s all over the place for the various supplies. Why didn't they use the same for that plus and minus 15? Well, yes, it could be due to the requirement for having an inhibit or something like that. Not sure, so I'm going to ignore them at the moment, hopefully anyway, and let's try and get that other supply, the isolated supply, that back end there up and running. So we'll plug in the secondary there. We'll start from 0 volts AC again and wind it up. And I've got a few test points in the board which I can measure just to make sure everything comes up okay. I'm not anticipating any problems there, but you never know. I've got the display disconnected at the moment. I do want to take it apart just to make sure there's no problem with the circuitry inside there. Okay, right, we've got multiple supplies to work with here. So let's just take a look. I'm going to go for the positive 1.5 first. Yep, I'm up at 120 volts and we're at 1.5. How about 3.3? It's coming up. The plus 5 volt. It's coming up. and the plus 60 volt. Yep, it's coming up as well. So let's get back to that 3.3. Let's try and achieve it. 180 volts. Got my 3.3. Nearly got to 5 volts. Let's go a bit further. 220 volts, 5 volts, perfect. 60 volts, not reaching it yet though. Something not right. Okay, let's try that again. I've got an Agilent multimeter hooked up across the secondary, which is generating that 60 volts AC. So I'm on the 60 volts DC output here as well. So let's wind that up and see where we get to. 240 volt. I'm getting 60 volts DC and AC there, but it is dropping off. But wait a minute. Of course I wasn't able to measure that 60 volt supply. It's a very high impedance supply, more than likely. Hence, with a multimeter, it was just pulling it down. So I suspect there's no problem at all with that 60 volt supply. I've achieved 240 volts. So I think actually we should try and hook up the display. But first, let's take the display apart and let's make sure it's okay before I plug it in and see what happens then. Well, that's absolutely beautiful, that is. What a VFD. It's got some burn in there by the looks of it, quite a bit actually. And actually there's not a lot to look at. There's no ICs or anything on this display. It looks like it's just driven directly via this interface here. We've got a tantalum capacitor there. It's probably the 5 volts or 3.3 volts, something like that, coming in. So I can check that, but let's put it back together. I don't think I need to be in here. Right, I think I'm ready for a power up. I'm just going to go for 240 volts straight off the bat. Display's all hooked up. I've wound it up to about 230 volts. That should be enough. And we should be good to go. So let's go. Yes, we've got a display. Will it get past initializing? That's a common fault. And yes, it does. Right, power's off now. I'm going to hook up my resistance box and let's see if we actually get anything on the display. Any accuracy at all. Does the inputs actually work? Okay, we're powering up again. I've got a 1K resistor hooked up. And we'll go into ohms. Now, overload again. I mean, the buttons are working. Nothing. So the inputs, none of the inputs appear to be working. Hopefully that shouldn't be too hard to fix. Well, there we go. I think we've done enough for this video. Call this a part 1. We've torn apart two 8846A Fluke 6.5 digit multimeters. And, well, I kind of got my faith in this older one coming back to life. Hopefully I can get to the bottom of it, but we'll leave that to part 2. And where we go with the other 8846A, who knows? Thanks for watching.